All right, this is a demonstration that I call Shells on Acid. And I find it's particularly useful for helping people understand why calcifiers, organisms like those shown on the slide that build their skeletons and hard parts from calcium carbonate, are particularly vulnerable to ocean acidification. Now for this demo, you only need white vinegar and a shell made of calcium carbonate. If you live near a beach, like I do here in Seattle, you can go down to the beach and collect a clam or an oyster or a snail shell. All of those will work really well. If you don't have access to a marine environment, you can try using a land snail shell. I've never done it, so test it first, but I think it should work. Or you can go out and purchase dustless chalk. Dustless chalk is still made from calcium carbonate. Modern chalk, I don't know what they're using now, but you can't count on it being calcium carbonate unless you see that it says dustless on the label. On the website where you found this video, you'll also find a PowerPoint presentation that I often show before I perform this demonstration. And I encourage you to watch the recorded presentation and also download my slides to use with your own audiences. In particular, this slide of the pH scale. I'm going to move this screen. I'm not sure if you can see this split screen, but I can. So I'm going to move it there. And in my presentation, I spend quite a bit of time introducing the concept of pH and this pH scale. So I'm not going to reiterate any of that here, other than what's relevant to the Shells on Acid demonstration. First, you should notice that vinegar, which we're going to use in this demonstration, is pH 3.0, 5 pH units lower than the pH of seawater. Now, if you watched my presentation already, you'll know that this means that the concentration of hydrogen ions in vinegar is 5 orders of magnitude higher than the concentration of hydrogen ions in seawater. Every solution listed on this scale has some amount of hydrogen ions, even those in the basic half of the scale, but the concentration of hydrogen ions increases exponentially as you move from the high pH end, or basic end, towards the low pH or acidic end of the scale. Hydrogen ions are what give acid its kick, and they can react with calcium carbonate and break it down. The reaction between hydrogen ions and calcium carbonate occurs much, much faster in vinegar than it does in seawater, because there are 100,000 times as many hydrogen ions in vinegar as there are in seawater. And that's why we're using vinegar in this demonstration today, because we haven't got all day to watch shells dissolve. You'll also notice that seawater is slightly basic. It's here at pH 8.1. This is the current average pH of the ocean surface. As we continue to burn fossil fuels and release carbon dioxide into the atmosphere and the oceans, that carbon dioxide is going to continue to react with seawater to form carbonic acid, which is what's shifting the pH of seawater towards the acidic end of the scale. And this is why, even though the pH of seawater is still basic, it is correct to say that it is acidifying, in other words, becoming more acidic than it currently is. Before the Industrial Revolution, the pH of seawater was actually 8.2. Humans' use of fossil fuels has already lowered the pH of the whole world's ocean by 0.1 pH units, and it will continue to acidify the seawater at an increasing rate until we stop releasing carbon dioxide, which is the waste product of fossil fuel combustion. As the pH of seawater declines, it's going to become more and more corrosive to calcium carbonate. Not to the extent that we're going to see in this demonstration, but certainly enough to cause serious problems for calcifying organisms like the ones you saw in the first slide. The last thing I want to say before we move on to the demonstration is about that term that I just used, corrosive. In the context of ocean acidification, it is correct to say that acidification is causing seawater to become corrosive to calcium carbonate, even though you certainly wouldn't call seawater corrosive if you put your hand into it. Solutions need to be much more acidic to feel corrosive to us. Even vinegar doesn't burn our skin, but you would notice if you were a baby oyster trying to build your first fragile shell in today's marine environment. Okay, let's get started with the demonstration. Stop sharing. There it is. Now, here's my oyster shell, and I'm going to put it in the solution and turn the glass so hopefully you can see what's happening. All right. When I immerse this oyster shell in vinegar, the hydrogen ions immediately begin to attack the calcium carbonate shell and break it down into its soluble components, calcium and carbonate ions. In other words, the hydrogen ions are causing the shell to dissolve. Now, the bubbles that started forming as soon as I dropped the shell in vinegar, which is acidic because it contains acetic acid, are a product of this dissolution reaction. They are actually carbon dioxide, which is formed when the newly released carbonate ions continue to react further with additional hydrogen ions in the vinegar. I'm going to pull this up close so you can see what's going on. Oh, it's a beautiful reaction. It's bubbling just like champagne. And you should pass the cup around to the members of your audience so they can see what's going on. And as you do that, remember to point out that what they see happening in the glass is not an accurate representation of what's happening in the marine environment now. We'll never see an oyster bed bubbling away like the shell in this demonstration. Because we're using vinegar, the dissolution reaction in this demonstration is occurring at a dramatically faster rate than it would in seawater. Even seawater with the extremely low pH levels that scientists have observed in Puget Sound, where the impacts of acidification have been particularly severe. pH levels as low as 7.4, 7.5 have been recorded recently in Hood Canal and Puget Sound. But in today's oceans, the problems faced by calcifiers like oysters, urchins, and pteropods is really one of bioenergetics. Simply put, as seawater pH declines, calcifiers are having to work harder and harder to obtain dissolved carbonate ions from seawater for their shells and hard parts. The increased acidity really makes those carbonate ions want to stay in solution. Excuse my anthropomorphizing, but the more energy calcifiers have to spend to maintain and build their shells, the less energy they have for other essential life functions like growth, reproduction, fighting off disease, feeding, and locomotion. And this is why acidification is so tough on them. Juvenile calcifiers seem to be especially vulnerable to corrosive seawater, and it's often at the juvenile stage where the impacts of ocean acidification are most apparent. Oyster hatcheries along the west coast of the United States saw this about 10 years ago, first started seeing this about 10 years ago, when their oyster larvae began dying on the second day of development. The second day is the stage at which the larvae, which up until that point look nothing like adult oysters, they're basically little swimming blobs of goo with a yolk sac. But on day 2, they have to undergo this major metamorphosis, converting almost 80% of their body weight into shell material. And they have to do this because until they can build this first shell, they're unable to feed themselves. They need to have something to hang their mouth parts from. And until they can feed themselves, they're subsisting on the yolk that was provided to them by their mothers as part of the egg. Now, on the second day, their gas tanks are getting kind of low. They're almost out of yolk. And if they can't complete this metamorphosis, they're going to die of starvation. So knowing what you know now, you can imagine how corrosive seawater was affecting the shellfish larvae, the oyster larvae in the hatcheries. Just needing to work that much harder to form their calcium carbonate shells in lower pH seawater that was being drawn into the hatcheries required more energy from the baby oysters than they had. And they died before they could feed themselves. Now, since that time, which will go down in history in Washington State as the Great Oyster Crisis, scientists have helped hatchery managers figure out how to monitor the seawater that is being drawn into the hatchery tanks and correct the pH of that seawater when necessary. But this is only a temporary solution. And as seawater becomes corrosive to calcifiers more frequently for longer periods of time, it's not going to be a viable solution. But even more importantly, correcting the pH artificially is not even an option for the vast majority of marine calcifiers that are not born in hatcheries, all those wild species that are living and trying to reproduce in today's increasingly corrosive marine environment. All right, that's a lot of talking for such a simple demonstration, but I wanted to make sure you had the background that you'd need to explain this well. I'm going to go back to one final slide. Here we go. Click through. All right, and move this down so you can see it. On this final slide is the website of Washington Sea Grant's ocean acidification webpage. You should be able to find this video, recorded presentations, PowerPoint slides, written up protocols of this demonstration and others. If you can also go to NOAA's source webinar page, which is where I debuted these videos, and obtain them through that program. To find the source webinar page, just Google NOAA, N-O-A-A, and source, spelled wrong, S-O-A-R-C-E, OA for ocean acidification. And you should get to that webpage, which has a lot of really great archived webinars all about ways to communicate and educate around the issue of ocean acidification. But one final plug for Washington Sea Grant, because I work for them. There's a whole lot of great stuff on our ocean acidification webpage, and I encourage you to go there. Thanks very, very much for tuning in.